Today we move to the normal distribution. Previously, we looked at the continuous distribution, right? And we first look at the normal, the uniform one. The uniform is has the density, which is very nice structure, right? It pretty much a horizontal line parallel to x-axis, and the area under the curve it creates the rectangular shape. Okay. And today we look at another distribution which is very popular. Okay, a lot of real data follow the normal very nicely. Okay, so say people at the beginning they didn't think they can learn the randomness. Okay, they cannot. They don't think randomness can be studied, but then they start to collect data like the weight of people, right? Height of people, something like that. And after they collect the data and they plot the data, okay, they plot and they can construct a histogram, right? And they find out something very interesting is that like the height, the weight, and a lot of different things. Okay, they observe it just follow in some type of bell-shaped fashion. Okay, which is start low, a lot of the observation in the middle, and end low. Okay, so like you see, maybe if we talk about the height of people, right? There are some people who are maybe so short, and some people are so tall, and most of the people will in the middle of the range, right? And that's the same for the weight of the people, right? And some people so light, some people so heavy, and a lot of people in the middle of the range, right? And then like they find out that actually some mathematician they would be able to rewrite the distribution, the density curve of this distribution. And today we have this is the normal distribution we learn. Okay, and after that people they find out actually we can study the randomness, we can study the uncertainty, right? Before that, they just think uncertainty is just belong to God. Okay, it's just a game of God, and no way for you to do such a thing, right? But eventually, with the development of science and these mathematics right, they develop those kind of tools, and people they find out actually even it's random, but you actually can learn that, right? Yeah. So the normal distribution, we did see it previously in chapter 2, right? When we talk about empirical rule. But today we look at in a more official way, okay? By look at everything about the properties, the form, how it behave, okay? So first of all, it's a yield to model continuous random variable, okay? So if you have continuous random variable outcome, and normal distribution is one very good candidate, okay, for you to use to model your random variable, your outcome, okay? We do have other names we call bell shapes because the shape it look like a bell, right? It's start low, symmetric, high in the middle, and end low, right? And also another name people sometimes they call Gaussian distribution because Gauss he king of mathematicians, okay, a king of mathematics world, and he did a lot of contribution to the field, and he's the one who showed that for a normal distribution it has a density like this shape. Okay, so in the first slide you can see that this the density shape for normal, mean mu, and standard sigma. Okay, so it will be just the core of this integral. Okay, so basically it's 1 over sigma square of 2 pi and exponential of x subtract mu square divided by 2 sigma square. Okay, so this is the density. Okay, for our class, we don't look at this, okay, because for our level, we just introductory level. We don't have to worry about that, but I just want to tell you, actually, the curve plotted in here, right, which it helped to create the bell shape here, is the form is 1 over sigma square of 2 pi and exponential of this quantity, okay? And then it has the characteristics of the normal is that it has outcome cluster toward the middle range, right? You have a lot of outcome in the middle range, and rest table off symmetrically to either extreme, right? And the notation here is that like for normal distribution, we need two quantity to specify the distribution. One is the mean mu, and another is the standard deviation sigma. Okay, yeah. So we do denote normal, which is n mu sigma. Okay, so which means like that normal distribution has a mean mu and standard deviation is sigma. Okay, and again to plot the curve, right? Like on the plot here, on the top here. Basically, it's just the density function is that, okay? 1 sigma square root 2 pi and exponential of this x subtract mu 2 sigma square here, okay. X subtract mu square divided by 2 sigma square here, okay. Here I just put it for completion, okay. It's not like you won't need to don't need to worry much about this thing, this PDF here, but I just put here for completion of the characteristic of the normal distribution. We do have some properties here. The range here go from negative infinite to positive infinite, okay. So it can go in the real value range. The shape here is symmetric because symmetric, so the mean, the median, and the mode will be the same, and they're all equal to mu, okay. And the spread, which is if you have bigger sigma, a bigger standardization, you have a flatter distribution. So in the plot here, you can see that we have 3 different normal curves with the same mean mu, but their standardization different, okay. So the red curve is that the standardization is 7, okay, and the middle curve, the standardization is 4, and the most pointy curve, the standardization is 2.5, okay. So you can see that with a bigger standardization, your distributions, you know, it become flatter, right? And with smaller standardization, 2.5, which is it's kind of the most pointy one, right? It's most pointy one. And we do remember that we do have the empirical rule where we again apply for normal data in chapter 2, right? Which it tells us like 68% of your data is one standardization from the mean, okay? So mu subtract sigma to mu plus sigma. 95% of the data will be 2 standard from the mean, and 99.7% of the data from 3 standardization from the mean, okay? So this is a rule we accepted as a fact, okay? As a fact in previous chapter. But actually, you know, after this chapter, you also can know where the 68, 95, and 99.7 come from, okay? Actually, it's just from some symbol Z transformation, and you should be able to get this number. And you get a more accurate number. It's not just approximately 95, 99.7, but your TI calculator can help you to get the exact number too. But here, like roughly speaking, we use this empirical rule, and it's acceptable, okay, to use that if you don't have the calculator, okay. But here you can also see one more thing that like with the 3 sigma, right? You can see that 99.7 your data from mu subtract 3 sigma to mu plus 3 sigma, right? So basically, it can tell you you don't have much data outside this range, right? So less than mu plus 3 sigma, subtract 3 sigma, bigger than mu plus 4 sigma, 3 sigma, and then basically at that time you just have about like 0.3% of your data, which is very relative small amount, right? So basically, like in some sense, you can think you just ignore that, throw it away, right? And if you look at outlier, at the time you need to look at the outliers. You need to look at those region, right? But more or less, if you just look at the main part of the data and the range from mu subtract 3 sigma to mu plus 3 sigma should be enough. For you to look at all the things you want. For some special cases here, basically like you have a normal with mean mu and standardization sigma. But if your mu equals 0 and sigma is 1, and at the time you have a standard normal, right? Standard normal, the Z distribution. You already saw it when you talk about Z score, right? The Z distribution. So basically the mean is 0 and standardization is 1, okay? So you have a Z distribution called standard normal, okay? And also, like if you have a X, we follow normal mean mu and standardization sigma. And if you standardize X, right, okay, which you do Z score strategy by subtract the mean mu and divide by standardization, okay. At that time, it will return to you normal 0, 1, okay. So if you have an X follow normal mean mu sigma here, okay, X follow normal mean mu sigma here, okay, and you standardize, okay, gives maybe, okay, give the standard, okay. Okay, so which means, okay, so basically if you X subtract the mu divide sigma, you get normal 0, 1, okay. I say, you know, with the sample data, you subtract the mean of the sample and divide by standard deviation, you also get the normal 0, 1, okay, normal 0, 1. So here you can see like you have a distribution of something with the mean 1 or 1, 0, right? And some standard deviation. After standardize, it will bring things to the mean 0 and standard 1. So let's look at the first example here. So we understand the distribution a little bit better. So newborn baby weight, okay? So it's a normally distributed with mean mu 7 pounds and standard 1 pound, right? So this is something you can obtain from empirical data, okay? Just randomly choose me 1,000 baby and you can get the mean and the standard shot, right? And here we assume that it normally distributed, okay? In reality, to know your assumptions are good or not, right? You just plot the histogram and you should be able to see that. But here we just make things easy for you. So there are two questions, okay? So draw a normal curve for newborn babies and shade the error under the normal curve to the left of 8 pound, okay? So first thing first. So our first task is that we have X will follow a normal 7, right? 7 and standard 1, right? 7, 1. So we need to draw a normal curve, okay? Normal curve, okay? So basically like to sketch that thing, okay? Basically you need to know what the mean, okay? And remember again, the 3 sigma rule tell us, okay, you have pretty much all your data from mu subtract 3 sigma to mu plus 3 sigma. And because in this case, your sigma is 1, right? And mu 7. So basically it tells us pretty much all your data from 4, right? In this case, mu subtract 3 sigma, which is 4, right? 4. And to the 10, right? 10, right? 10, which is mu plus 3 sigma, right? So basically, like you can draw like this, right? Draw a bell shape. Okay. The software can do it for you more accurate, okay, than me, but my drawing is not good, but it's acceptable, okay, here, okay. But basically, just make sure you have symmetric kind of bell shape, and the range will be pretty much like dense, narrow, focus, everything in from 3 sigma, right? But more or less, it should be like this shape, okay. So if you do the software, okay, it can draw for you very accurate, okay. But here I just kind of sketching, okay, sketching. So draw a normal curve for newborn baby weight, shade it. And then the second task, so this is a normal curve I have, right? And if you plug in your calculator, you need to plug in this function, okay? 1 divided by sigma, which is 1, right? So if I plug in the function, basically my this is the curve here. 1 divided by sigma, which is 1 already, so 2 pi, right? So 1, we don't write it again. And exponential of negative x subtract mu, right? 7 square by 2, okay? So if you want to draw the exact curve, okay, so then basically you need to ask the computer, right? Maybe you ChatGPT, whatever tool, right? To draw this curve, and it will show you exact curve for this, okay? So now what's the next task? Shade the error under the normal curve to the left of 8 pound, right? 8 pound. So to the left 8 pound, so which means 8 here, right? So this is the error, okay? Okay. So this is part A. And suppose that the error under the normal curve to the left 8 pound is 8.41, okay? Provide interpretation of this result, okay? So what if, okay, we learn how to find the error soon, okay? But what if, okay, so in part B, they ask us, okay, what if the shaded, okay, the shaded region, okay, the shaded region, okay, the area of that, right, area of that equal to pi 0.41. So what does it mean here? What does it mean here? So the shaded region, basically, it's just a property of x, right? X less than 8 pound, right? Less than equal. It doesn't matter, right? The equal sign not matter in the continuous distribution, okay? Right. So what we have here. So what does it mean here? So x, what is the x here? X is the weight of a newborn baby, right? Weight a newborn baby. Represent newborn baby. And we have probability X less than A equal to 0.841. So what does it mean? Interpretation here, which means basically like for a randomly chosen baby, right? Randomly chosen baby, right? The probability, right? Probability, his or her weight, right? Her weight less than at most, okay, it doesn't matter the equal sign. 8 pounds is 0.841, right? 0.841, okay. Maybe 84.1% of the newborn baby has the weight than 8 pounds. Okay, the same thing. It just tell you about the same thing, right? 84.1% of the newborn baby have the weight less than 0.8. Maybe we can say for random chosen baby, right? The probability his or her weight less than 8 pounds is less than at most, okay? Just the same thing here, okay? Because the equal sign does not matter, right? Is 0.841, okay? So this is how you interpret this result, all right? Based on the error under the curve, you can see the error under the curve, and you can get the interpretation here, okay? Another example here, talk about SAT score, right? And here we revisit the standardized thing, right? We just saw. So here are the distribution of SAT score student at school in normal distributed, right? With the mean of 1,010 and standard 30, okay? So this is the SAT score, okay? So the first question is that what is the median of SAT score, okay? And the second question is that like if you standardize all the SAT scores by converting them to Z distribution, so basically you just subtract the mean and divide by standard deviation, right? So find the mean and standard deviation of the standardized score, okay? The two questions, okay? So the first part is that what's the median of SAT score? And to answer this question, like basically like we just look at the property, right? The normal distribution is symmetric, right? So basically the mean and the median will be the same and also the same as the mode 2. So in this case, the mean equal to the median and equal to 110, right? And in part B, after you standardize all SAT score, okay, by converting them to Z distribution and find the mean and standard deviation of the standardized score. So this again, because you already can standardize them, right? Which you bring to Z distribution. And remember, the Z distribution is a normal 0, 1. So which means the mean now is 0 and standard deviation is 1, okay? So this question, again, it just, make used to look at the property one more time, okay, to think about it more thoroughly, okay. What happened with the median of the normal distribution, and what happened after you calculate this score for your data, right? You should expect after you do the standardized, right? You get the mean 0 and standard deviation is 1, right? And finding this score is also a very important thing, right? And people, they love the Z distribution. They want to, a lot of time they want to translate into the Z score because it makes things like comparable across the data set, right? So again, we talk about the example, right? An ant and an elephant, right? Who more extreme? Maybe a person who grow banana and a person who grow apple, who do better job, right? In order to compare banana and apple, you need to standardize, right, with their own data, right? Their own data, and in order to make that comparable across the data set, okay? So now we look at two things, okay? Typically, like these are two important things people want to know, right? And it related very closely to the chapter 2 with this C, okay? So here, like two common interest question, right? As in chapter 2, we did say. So here in this case, but we look at a normal, okay? So the first question is that we given a value B, okay? Find the property X less than equal B, okay? X less than equal B, okay? So if you have value B, what's the probability X less than equal B, okay? And what is that probability? So say, for example, like, you are 5'8", right? Tall, right? And like what's the probability a random person in the US, right? Shorter than you, right? Basically like where you stay in this population, right? In terms of your height, right? So basically, like it's just pretty much like the same question as in chapter 2. Given a value x, right? Find the percentile tied to x, right? Tied to x. So it's just the same thing. And the second question is that like given the error under the curve E alpha and find the value B such that okay, probably x less than equal B equal to alpha. Okay, so this is another question. Basically, like you have the error and you want to find the value. Okay, so basically say you were wondering what's the median income in the US, right? Median income, household income, right? So at time the error under the curve will be alpha equal to 0.5. So basically you need to find the value, the median income, right? Maybe you think what is 90% Thai income in the US, right? So which is the error under the curve will be 90, right? 0.9, right? And you find the value, okay? So the remaining of this class, we will look at these two kind of question, right? Okay, and we will do with different examples to understand this clearer. Okay, and also it just tie very closely to number 2, which you have the percentile value and you want to find the x, right? So we did have that already in chapter 2, but now we look at it's more official for the normal case. Okay, for normal data case. Okay. So for the first question here, okay, so say given a value a, right? Given a value a, I'm sorry, a here. Find probably x less than or equal a, okay? So basically you have a normal curve like this with mean mu, and you have a value a, right? And find the probability x less than or equal a. So in the plot here, right? Basically it just shaded error here, okay? Everything less than a, right? So it's the light blue here, the blue, okay? Luckily, okay, your TI calculator can do it for you, very good, okay? So basically if you have a normal mean mu standard sigma, okay? And if you want to do that, you just do something called normal CDF, okay? Normal cumulative density function from negative infinite to the A, okay? So everything up to the A, okay? And you provide the mean and the standard deviation, and then it will do that job for you, okay? But because your TI calculator, okay, it doesn't understand what is negative infinite mean, okay? So basically you need to fit it in a number, okay? To fit a number in. So there are different strategies to fit in your TI calculator this value. One strategy is that you just replace by anything from mu subtract 4 sigma and below, okay? Because why? Because we did say that pretty much all your data from mu subtract 3 sigma to mu plus 3 sigma, right? So if you go from mu subtract 4 sigma and below, you should be fine, okay? You should be fine. But another tip here is that often I don't do that. For me, I am lazy, so I just put negative 9999, a very small number, okay, to replace the negative infinite, and it works most of the time, okay? And then we also do have other modified version. So say find the probability x greater or equal than a, okay? So previously x less than or equal a, but now x from a and above, right? So at that time, it will change a little bit by doing a normal CDF from a to a big number, okay? Big number and mu sigma, okay? So the big number here, again, you can replace by any number from mu plus 4 sigma, or the tip here, you just plug with 99999, something like that, okay? So it should work for you. I'll show for both cases what happens if you replace by mu subtract 4 sigma and negative 999, maybe replaced by mu plus 4 sigma and 9999, okay? Question? They don't have it. So this is why I'm telling about the trick here, okay? We don't have the infinity button, okay? And the computer, it won't understand that thing, okay? Yeah, okay, yeah, no worry. Yeah, this the computer only understand 1 euro, 1 euro, 1 euro, 1 euro, okay? So if you put a negative 999, it will translate to a 1 euro series in some way, okay? And it calculate that. So basically, like, you should know that the computer only understand 1 euro, 1, which you have electric there. Euro, you don't have electric there, and it's perform the calculation for you, okay? Okay, we have in the next example, okay? Here, this slide, I just present the general thing, okay, formula. We have example 613. It will tell you everything about that. Thank you, Ashley. Yeah, keep asking, okay, because if you're confused and then it won't work, right? And then it just make you feel very more, right? So here again, if you have the modified version here, x greater than or equal to a, you should do a from bar to infinite. And the tip here is that because your calculator don't know what is bar to infinite, right? So you can replace by any number from mu plus 4 sigma and above, okay? Or you can put 999 most of the time. 999, right? 3 number 9, 4 number 9. It should work most of the time, okay? And last one, which is find the property x belongs to between a and b, right? So last time it is easy, right? Just plug in normal CDF, the lower bound A, upper bound B, and then mean standard deviation, okay? So if you have a newer version, this thing will be very clear, okay? But say if you have TI 83 and older version, you should be very clear about the order, okay? It has to be that order. Otherwise, it just mess around. It doesn't give you the right number, okay? So let's look at the example to answer Ashley's question, okay? So here, US adult pressure, okay, blood pressure. So here, like from empirical data, right, we can see that US adult blood pressure are normally distributed, okay, with a mean 1 to 8.4 and standard 19.6, okay. So the question here that for any randomly chosen US adult, right, find the property that the chosen person had blood pressure less than 122, okay. So this is the first question, right? This is the first question. The second question, which is greater than 170, and the third question is between, right? So basically it's corresponding to 3 cases, right? The first case is less than, the first case less than, the second case bigger than, right? Greater than, and the third case, right? So we walk through it, okay? And you see what happened in here. So the first thing first, right? If you didn't know X is the blood pressure, okay, of a random chosen US adult, right? And then we did see that it had the normal distribution with mean 1 to 8.4 and standard deviation 19.6, right? So which means in this case, you already have it here. X follow normal 1 to 8.4 and 19.6, okay? So the first question, okay, if you choose one US adult, right? What probably his or her blood pressure less than 122, right? So basically at that time, it is the first problem, right? It's the first problem here. X less than equal A, right? Remember again, for continuous distribution, the equal sign does not matter, okay? You can throw it away, okay? You don't have to worry about that. So in this case, you do normal CDF, negative infinite, right? Negative infinite, A mu sigma. But again, we can use the tip, right? The tip. But here I put the negative 999, okay? Negative 999. I can also replace by mu subtract 4 sigma, okay? I will show both way for you, and this way you can see both ways should give you the same number, okay? Pretty much very close, okay? Very close. 4 sigma, which is 4 times 19.6, okay? So I can use this number. Any number less than this number, you just negative 999, okay? So most, typically I just use negative 999, okay? So let me show you how you do that in your TI, okay? TI calculator. If you have your TI, just put out and, do it with me. So this way you learn fast, all right? You don't need to go home and, look at the YouTube, right? So second here, distribution. You do normal CDF here. So low bound, in this case, my calculator is very generous with me. It only give me like negative 1 0 0 0 0. You have 99 number 0, okay? But let me just replace it by negative 999, okay? So here, one thing you need to pay attention, okay? Don't use this sign, okay? Not use this sign. Do not use this sign, okay? This is a subtract sign. If you use, but let me just, say ignore my warning, okay? And use this sign and see what happened, okay? 1 2 2, right? Yeah. So 1 2 2, 1 to 8.4 and 19.6, right? 1 to 8.4. The meaning 1 to 8.4 here. 0.4. And then 19.6, right? 19.6. Okay, so if I do that, okay, here I put the negative sign as this sign, okay, which is wrong choice. So I'll show you what happened. You see, it error, okay? It won't understand, okay? You have to use this sign, okay? This is a negative side, okay? This is subtract, okay? This is subtract. The negative side is this side. So now you just go back here, okay? Quick here, maybe 1. Do it again here to make it correct. Normal CDF, okay? So this has to be like this, okay? Negative 999, okay? Okay, 9.6 here. You see, now you get the probability 0.372, right? 0.372. So this is one way you do that, right? By just plug in negative 999 to replace for negative infinite. Another strategy is that replace the negative 999 by any value from mu subtract Force man below, okay? So this is another strategy. So what happens if we do that, okay? So now the mean is 128.4. And subtract, right? 4 sigma, 4 times 19.6, right? Yes, so you can go this way as well. It's up to you, okay? So you can see it's very close, right? It doesn't show much difference between these two, okay? But I would suggest, for my myself, okay, I prefer the negative 999 thing because I don't need to think much, right? I don't need to think much. Question? Yeah, so basically it just calculate the normal CDF here, right? Is that what you're asking? Oh yeah, that's call. Yeah. So what Ashley is asking is that she's one with more mass. Yeah, we can discuss if you want to calculate this thing. So basically, like she's asking, like, is that calculate this area here? Yeah. So say basically say you think this is 1 to 2, right? And calculate this. And basically you do the integral like this, just like integral from negative infinity to 1 to 2, 1 over sigma which is 19.6, and exponential of this thing, and it's do that thing here. But for sure, yeah, if you want to go to that level, just take my class, okay? I teach math for 130 next semester, so and hopefully I can teach some AI class eventually too. So if you care about that thing, and then yeah, you can enroll for more advanced class, okay? But here, like, I just introduce for completion, okay, and maybe encourage some of you who want to go to data science career, whatever, okay. Yeah, very good question. Yeah, it does that job. In fact, this integral cannot be calculated by hand. Okay, so if you trick some maybe high school student, you give them this integral, and say I will give you maybe $10,000 if you can calculate that for me, and you just need to pay maybe $2 for me or $10. If you cannot do that, they won't. It's not something you can calculate it. With manually. Okay, it needs a computer to do that. You need to approximate. Okay, this is not doable. Okay, so this is sometimes when I teach in high school, I trick my student. Okay, do that, and you get bonus. Okay, otherwise you need to do the homework. Okay, and some students, they try to do that, but I think the best guy, he did a week or something and he gave up. Because I know it's not doable. Okay, I get that kind of training already, so I know. But because he in the high school level, and so he didn't know about that. So it's good to know. Okay, something is not like you can always solve it, right? This is why we need to appreciate the computer science people. Okay, so the last one, right? There's a second one, right? X greater than 170, right? So in this case, you just do normal CDF, 170, and anything be but infinite, right? And again, just use trick, right? 170, a big number here. 999, you put 999. If you're more careful person, you may put 4 number 9, 5 number 9, it's fine. It should affect much more the result, right? At that time, you can also get this property. So let me also show you again here. We just walk slowly here, okay? Because you will do this thing many times from now on, okay? Yeah. The normal distribution is it kind of the golden time distribution, the most important distribution in statistics. And so this is why you see it a lot, okay, from either the basic level or the advanced level, okay. So you put 999 here, same thing, right? Which is the lower bound is 170, upper bound is positive infinite. But again, because your calculator don't understand what is positive infinite, right? Yeah. So you get like 0.017 here. If we round up, keep 3, right? 0.017. But again, you can also put a 4 mil burst for sigma. Let me just make it slower here. By do mil burst for sigma, right? So in this case, you do the lower 170 and the upper you put like mil burst for sigma, which is 1 to 8.4. Right? Plus for sigma, which is 4 times 19.6. Okay, so you get also the same, right? 1679, right? 017 if you keep 3, right? 017. And similarly, right? What property a random chosen US adult has blood pressure, right? From 100 to 150, right? 150, right? So you also give the, in this case, easy, right? Easy. So just low about 100, up about 150, and everything the same, mean and saturation, and your point 1791, right? So from here, you see that, with this data keep track, right? Blood pressure people, right? So you can see it's very rare, right? With a very low probability, around the chosen person has a blood pressure greater than 170, right? So they do have some application in just nowadays, right? But especially for some older people, they live in some countryside, right? And they cannot get the support very quick, right? From the medical side, right? So say now they just wear some kind of wristband, right? And from that, the data will keep track. The system will keep track of data, right? It just send to their phone, and they keep it in the system, right? And maybe it's just one day or something like that. They see some weird thing about blood pressure, right? So maybe 171, something like that, right? And which is pretty rare, right? So which means something wrong. So they can give the call directly to you and save your life. Okay, that's so they do have a lot of application in just in time medicine now. Okay, Harvard, they have big team doing that. Okay, keep track people data where they wear some kind of smart watch device, and the data to keep pushed back to the system, and it just manage it automatically. Okay, if they see something weird, strange, and they define. So for example, here, like in case see the property of a person, have a blood pressure more than 170 here, it's about 2%. If you cut off 5%, it's low, right? It's low side, which means something wrong with that person. So they just directly pick up the call and see, are you okay? You need help or whatever, okay? So this is something they do apply in the real life, okay? By keep track of the demographic data and then help the people, the society healthier, okay? Healthier. Oh, where? Show your calculator. Okay, yeah, okay. Let me see. Okay, show you one more time. Okay, yeah, it's good. We need to walk it slowly. This way, when you go. So second here, okay, and then distribution, right? So the second, it will show up anything in blue, right? So if you have blue, you want thing blue. Second mode here, it will show you a quick, right? Second vast here, it shows you distribution here, okay. And you go to normal CDF here, right? So for example, you want to show the part C, right? From 100 to 150, right? So which part is show you the error? A, B, or C?
It doesn't, just like when I put it in and like I hit enter and then hit enter again, it just says error.
Let me show. Okay. Okay. Okay, so see, this way, you need to practice, right? Otherwise, you go to the test room and and you cannot get it right. The second question is that you have the area under the curve, okay, which is alpha, and you want to find the k, right? Find the k. I'm sorry, find the k, such that, okay, probability of x less than or equal to k equal to alpha, right? So say if you care about like 50, but what is the median income, right? A median height of people here, right? So at that time, yeah, alpha is 0.5, right? And then basically you need to find the k such that probably x less than or equal to k equal to alpha. And in the plot here, we have alpha at 0.9, right? So why a 90% high value of the height of people in the US, right? So basically, you need to find the k, right? So that probably x less than or equal k equal alpha, right? blood pressure, right? What the 90% type of blood pressure, right? Of US adults, right? And then you have 0.9, right? And you need to find a K. And luckily, also your TI calculator can do that for you by using inverse norm function, okay? So basically what you need to do is that you need to fit the error, okay, alpha here to the TI, and you give, okay, you tell it, okay, my distribution has the mean in mu and standard is sigma, okay? And at that time, it will show you this K value. And the function do that, the order with second variance, and inverse norm, okay? Alpha mu sigma, okay? And again, we do have other modified version, okay? Because, people like, they smart, right? They think about all different thing, the kind of thing, right? So now say, we don't want, so here basically it's on the left side, right? Left side, right? The error on the left side of K, right? But what if some people, they say, okay, now I don't want the left, I want the right. Okay, find a K such that probably X greater than equal than K equal to alpha, okay? So in this at the time, okay, if you have a modern, okay, the later version, DI84 or DI89, okay, so modern version, you don't have to worry about that. You can do that very easy, okay? But from what I see, most of you here, you have the DI83 or DI84 is the older version. So basically, you need to do a little bit work here, okay? So basically, like, in order to do that, because your TI with the older version, okay, it can only do the left tail, okay, left side here, okay? So basically, in order to get this thing, which is the right side here, X greater than equal than K, you need to do a little bit labor by making this transformation, okay? Probably X greater than equal K equal to alpha. So which means less than K will be 1 minus alpha, okay? 1 minus alpha. So which means that now you bring it back to the original problem, okay? Original problem. So which means K equal to inverse norm of 1 minus alpha mu sigma, okay? So let me just show this slide for you, right? So hey, here, right, the same thing, right? So you have like the K here, find the K, right? The K such that, right? So now say, because it's a right side, right? Find K such that probability X greater than K equal to alpha, right? So which means the left side will be 1 minus alpha. Remember, the total under error under the curve must be 1, okay, to make it satisfy property, right? So which means less than K is 1 minus alpha, or at the time it come back to the original problem, right? Yeah, K just the inverse norm of 1 minus alpha mu sigma, okay? So if you have older version of TI 84 or TI 83, this you must do, okay? If you have a newer version, and then it just take care itself by telling the calculator, okay, I want the right tail, I don't want the left tail, okay? So it depends on which calculator you have, okay? And the last, another modified version is that like find two value A and B, okay, symmetric around the mean, okay, such that, okay, probability X belong to A and B, okay, equal to alpha, okay. So at that time, again, if you have a newer version, you don't have to worry. You just need to tell the calculator, okay, I want a center error equal to alpha, and you're done, okay. But if you have an older version, then you need to do some more labor by doing this transformation, okay. So basically what we have here that the error between A and B alpha, okay. And remember the total error under the curve is 1. And we also have a symmetric nature, right? So which means the left side here, dot here is 1 minus alpha by 2. And here you also have 1 minus alpha by 2, okay. So which means the two sides here, it contribute to 1 minus alpha, and plus alpha in the middle, you get a 1, right? So which means probably X less than A equal to 1 minus alpha by 2. And at the time, it brings you back to the original problem, right? Just invert norm 1 minus alpha by 2 mu sigma. And also, you have the error, the dot on the right side here, right? Probably X greater than B equal to 1 minus alpha by 2. So which means it translated back to the second case, right? Second case. or probably x less than b will be 1 subtract 1 minus alpha by 2. So which means at that time your b will be the inverse norm of 1 subtract 1 minus alpha by 2 mu sigma, okay? Mu sigma. So this is how you find A and B, okay? If you have older version of calculator, okay? But if you have a newer version, you just tell, okay, I have the error in the center, okay? E alpha. What is my A and B? You just do inverse norm and it shows you. So it's for you, okay? So let's look at the example. Okay. And we see how we use the inverse norm function, okay? So again, we have the real data from Guinea-Big's tooth growth study, right? So length tooth growth of Guinea-Big's is normally distributed, right? With mean like this and standard deviation, right? So if you already know x is the length, right? And basically your x is the length tooth growth, right? And then your x will follow a normal with mean 18.81 and standard deviation is 7.65, right? 7.65. And what is the Q3 value? Q3, which is the third quartile, right? At the 75 percentile value. So at this point, you should know what is Q3, okay? It's just a third quartile at the 75 percentile value, okay? So basically, we want to find the K, right? Such that probably X less than equal K, okay? Less than S equal doesn't matter, okay? And because the equal sign again, it does not matter in the continuous distribution, okay? So basically, your job in A is that, right? And at the time, we know that we can use the inverse norm function, right? If you know x is the length tooth growth of Guinea-Pigs, right? And then x follow this. And your K is your Q3, right? Less than 0.75. So which is the Q3 will be inverse norm of 0.75, 18.81, 765, okay? So let us do it together, okay? So you do the second again. An inverse norm, right? Inverse norm. So you tell, okay. Oops. Maybe quick it, okay. Second. Whereas and then inverse norm, okay. Oh, what's doing here? Second. Inverse norm, okay. Inverse norm. So the area is, this is a newer version of calculator. So, you know, I don't need those transformation. But anyway, I will just show you here. 75 here, okay. I'll show you all the way, different way to do that, okay. Now I just stick with the left one, okay, the tail left. So the older version, it only can do with the left tail, okay. The newer version, it can do for different kind of thing, which we don't need the transformation. We just told you, okay. So 18.81 and 765. 18.81, 18.81 and 765, right? 765. And make sure we have a left, right? Because probably x less than that value equal here, right? So it's at 23.6 969, which is 97, right? Inverse norm 18.81 765, right? 18.81 765, right? So yeah, 23.97, right? Which is correct number here, right? Correct number. The same thing, right? Here the 30 percentile value, okay? The 30 percentile value, it is 30 percentile value, right? The length to grow separate the 30% at top, right? Bottom 70% at top. Okay, so we look at this type of question, we should be able to realize that it's just the 30 percentile value is what they're asking for. Okay, so we do inverse norm and we give the error to the left, right? Inverse norm here. Here, which is 0.3. The same thing is 14.798. 14.798. Yes, okay, that's correct. Now, in the last question, right? The last question, which is find A and B symmetric around the mean, okay? Such that, you know, we have 92% of the data follow belong these two values. So we return to this problem, right? So in this case, our alpha is 92% upon 92, right? So we just plug in. So in this case, your 1 minus alpha will be 8%, and 1 minus alpha by 2 will be 4%, right? So which is 1.04. So you can do, yeah, I think we did show this calculation, okay? Probably x less than a. So here we calculate. We show the calculation again. So in this case, you can see probably x less than a is 0.04, right? And x greater than b also 0.04. Because the total is 0.98, that's 2, right? It would be the two sides we add up like 0.08. And because the matrix, it would be each side be 0.04. So in this case again, probably x less than a equal 0.04, which means a will invert norm. Okay. Oh, there will be something here. X equal 0.04. I think I think here 0.04. Okay, so which means your a here. So just back here one step. Okay. So a will be invert norm, right? Invert norm of 0.04, 18.81, and 765. Okay. And if you plug in your calculator, you get this value. Okay. And again, the same for B, right? B, you can also get it for doing invert norm of 0.96. Okay. So for B here, you see that because x greater than B is 0.05, 4, which means x less than B is 0.96. Okay. So if you have an old calculator, okay, older version, this is how you go with it to find a B, right? But if you're lucky, you get a better, much better computer calculator, right? And then basically you just directly can directly find the question, okay? B a less than equal x and b equal 0.92 by doing and don't need to do this much labor by doing the following, right? So here, let me show you. Invert norm and you give the error 0.92 mean solution is the same, but here we put center. That's it. So you understand you this problem, you see. So it gives you your A here 5.417 and your B is 32.203. Okay, so very good here. Yeah, very fast, right? So let's look at this problem together, okay? Cookies filling process. A bag of cookies is underweight if it weighs less than 250 grams, okay? And the filling process dispenses cookies with a weight that follow normal distribution, which means 260 grams and standard 4 grams, okay? So this is something when, people, they produce a machine, okay? They keep measuring things and they can come up with this data, okay? And here we assume that they follow normal distribution. So first, find probability that are randomly selected back underweight, the underweight, right? Back. Okay. So let's just maybe solve the problem together one by one, okay? So underweight, what does it mean underweight here? Which means in this case, say less than 250 grams, right? So first, let's insert one slide, okay? We do the problem together. So the machine, it filled with the normal 260 and standard 4 grams, right? So if we do X in the way of a random bag, right? Random bag. So your X will follow a normal mean 260 and standard 4 grams, right? 4 grams. This is what we have. And find the probability randomly selected bag underweight. So underweight, which means X less than 250, right? Again, the normal the equal sign not matter here, right? So which is normal CDF, right? A very small number, I put something like this, 250, and the mean and standard deviation. Okay, we can do that with the TI calculator, right? Calculator. So this key will be normal CDF. Negative 99 to 50 to 60 and 4, which is 0.006, right? 0.006. Okay. The second question, what is that? The body proportion of the cookies are more than 2 standard deviation above the mean. Okay, so what is 2 standard deviation above the mean? So which is 2 standard deviation above the mean, which is 60 to 4, right? 268. So they want us to find the property of a random chosen bag weighted more than this much, right? 268. And we can also do a normal CDF. 268, a huge number, put 999 here. 264, okay? Normal CDF here. 268, which is bigger than this 999. Okay. Which is 0.023, okay, 0.023. So this is a B, this is A. C, how many standard deviation under weight is a cookie that weighs 250.3 grams, okay? Now here, bag of cookie, right? A bag of cookie, a bag of cookies. So in this case, it's just pretty much the Z-score type problem, right? So you have a bag of cookie where the weight is 250.3. You want to find how many standard deviation under weight, okay? So you bag of cookies, right? So what you do with this problem is that just using value, subtract the mean and divide by standard deviation, right? And this you can see how many standard deviation under the mean. So in this case, you have a bag cookie 250.3, and basically you calculate this score, okay? 250.3, let's do it. 250.3 subtract 260, and you divide by 4, okay? So 2.42, right? So negative 2.42. 2325, right? So which means for a bag cookie that weighs 250.3, is under weight the 2.425 standard deviation below the mean value. Okay, so the negative value, which means it's below the mean. Okay, if you have bounded value, in this case you have above the mean, right? It's overweight, but this bag is underweight. Underweight. And what's the last question here? What weight represents the 99 percentile, right? Let's say, we want to find the weight, right? Where that weight, 99% of cookie filled by this machine has a weight that value, right? Less than that value. So easy. This for D. Basically, what they want to ask is that find the value 99 here, such that this property is 99, right? So this is just the inverse norm function, right? For 99, the mean is 260 and 4, okay? So we can solve that. For 99, 260 and 4. And now remember to return to the left, right? Because we talking about first the percentile, right? It has to be left. It's 260.305, 269, right? 269. So in this case, P999, I write it here, okay? 269.305, okay, 305. So which means 99% of your cookie bags filled by this machine will have the weight less than 269.305. Okay. So far, this with this value, you can see that say you maybe one beautiful day, and then you are the manager, right? And you randomly chose a certain bag cookie, you see all of them weigh more than maybe 270, and then you need to talk with the maintenance team, right, to investigate what's happening, right? Because we should expect that 99% of your bag, cookie bag should weigh less than this value, right? But if the machine overfill the cookie, right, which means that there's something wrong, you need to stop, they need to do some investigation. Otherwise, you won't make a lot of benefit, right? So if your machine keep overfilling, right? But sure, if it underfill, it also like a problem, right? A problem, because you may get complaint from customer, and this is something you don't want. So here, the quiz 6.11. Okay. Now assume that human body temperatures are normally distributed. Okay, with a mean 98.6 F and standard 0.63, right? And normal the 98.6 and standard 78.63. The first question is that what percentage of human body temperature less than 98.6, right? So in this case, you can see it's just the kind of problem where you give a value, right? And you find the percentage of the error under the curve, right? So Px less than equal 98.6, and now basically what you have to solve the problem is the normal CDF function, right? From very small value and to 98.6, and mean 98.6 is either 0.63. Okay, so you can solve it. But for sure, if you on second part of this problem, the value 98.6, they ask you to find exactly the mean value of this problem, right? So which means you don't need to use a calculator. Oh, because the mean and the median is the same, right? For the normal distribution is symmetric. And because the mean and the median is the same, and because the mean median is the same, basically we should expect to have 50% of the data, right? You see in this case, the percent will be 50%. And here, the question is what the temperature separates top 5% and the body bottom 95%. In this case, it is finding the 95% high value, okay, 95%. So be very careful when you reach the center, okay, 75%, 95% and bottom. inward norm of 0.95 means any standard deviation. So it's very simple to solve this quiz, right? So the last section is class A about critical value case. So if we have a z distribution, normal 0, 1 for some small alpha between 0 and 1, then universally we will choose 0.05%, okay? Some terminologies, okay? First, z alpha. Z alpha is the 100 times alpha percentile with z, okay? And z1 alpha, 100 times 1 subtract alpha percentile with z, okay? And here we have another terminology, so this is basically just a percentile value, okay? So for example, like if alpha is 5.05, right? So 3.05 is the 100 times 0.05, which is the 5% division of Z, right? In this case, yeah, 1 alpha with 0.95. So this is the 95% division. We have a definition called critical value. This is a cut-off value to make the statistical decision. Okay, you see the critical value, you use it a lot in later chapter when we deal with hypothesis testing. Okay. Learn how to find this value. Okay. So we notice that the z alpha here will be inward norm. Okay, alpha 0, 1 because it's an alpha percentile value, right? 100 times alpha percentile value. And also you can find z1 alpha by doing inward norm, okay? And here the fact, okay? Because the z distribution is symmetric around the mean, okay? Around the 0, 1, okay? So basically in this case, you can have that z1 alpha equal to negative z alpha, okay? We don't do it here, but it's a fact, okay? So here an example 6.6. Here we want to find a critical value 3.95 and 3.05. Okay, we show the result, okay? So just 3.95, just very straightforward, right? The 95% high value for a z distribution. And for a z distribution, you have the mean 0 and standard deviation 1. So which means in this case, you just do inward norm 0.95, 0, 1, and you use 1.645. And on setting for z05, 0.05, okay, you just do inward norm 0.05, 0.1, and you get a negative 1.645. Okay, so again, you can confirm with the fact in the green, I say the green, right? I highlight green, the green here, which means the opposite position, okay? So how we interpret this number? So z0.95 tells us 95% of the values in the z distribution less than 1.645, right? And also setting 5% of values in the z distribution, standard model distribution, less than negative 1.645, okay? And last slide here is attention, okay? So there's some difference between my notation in my lecture note and in the textbook we use, okay? So our lecture note, we know that z alpha is 100 times alpha percentile, and z1 alpha is 100 times 1 alpha percentile. We use that to make it very intuitive and you don't have to confuse, okay? But, and it will help you a lot for confusion in the future chapter, okay? You see that. But the textbook and a lot of references, you may see that they may know z alpha equal to inverse norm of 1 alpha 1, and then z alpha equal to inverse norm of alpha 1. Okay, they do that because they try to make you the fact of z alpha and z1 alpha the opposite in the sign. Okay, but to me, okay, I prefer to stick with the notation I introduced you, because I think it will help you to avoid the confusion, okay, eventually in later chapter, okay. So it depends, if you prefer this the notation I use, you use it, okay. But you should be aware that the notation in the homework, quiz, or the textbook you read may slightly different with what I denote here, okay. But if you don't prefer the way I do the notation here, you just keep consistent with the homework with the textbook. Okay, either way it should be fine. Okay, but for beginning level, I feel like the way I denote as I introduce you, it gives you a better way to avoid confusion. Maybe some wrong mistake in calculation eventually. Okay, so thank you so much for your attention. I look forward to seeing you in the next chapter.